Hi friends, today you're getting the extended cut of logarithms. Logarithms are great mathematical tools. If I'm trying to solve an equation that has a variable, an x, and an exponent, if I'm trying to solve the equation 3 to the x equals 81, and I don't know what exponent that is, I'm asking a logarithm question. What I'm basically asking for is the base 3 logarithm of 81, which if you have a calculator where you can enter those things, you can type that in and you should get 4. You probably could have come up with that. If you tried 3 to the 1, 3 to the 2, 3, right? You'd eventually get that 3 to the 4th equals 81. But where logarithms get really helpful for us is what if I said, I'm trying to solve the equation 3 to the x equals 10. Now, x is not a whole number. It's not even a rational number, but 3 to some power will equal 10, and our calculators will be able to compute what that number is by using logarithms. So logarithms might seem scary. A lot of people don't like them, but they were incredibly helpful. And this is your rule of thumb. If you don't have this written somewhere in your notes, take a minute right now and jot it down, because this little synopsis here will tell you how to define logs, what the expression logarithm means. So if I asked you, for example, for the base 8 log of 64, what I'm asking is 8 to what power, 8 to the x, equals 64, right? That reframes the expression for you in a way that's a little bit easier to understand. All right, so properties of logs are what this video is really about. I would call these log laws. And the properties of logs, there are 3 properties of logarithms that allow us to rewrite or manipulate log expressions to look like something different, even though it would be equivalent. And they are helpful for us in a lot of ways, and you just kind of have to be fluent with them. All right, sometimes people go, I don't understand the log laws. Like, well, you can understand them. I'm going to explain them here in a second. Like, there is a basis for where they come from, but this is less about like getting it and more about just being able to do it. In the same way that like when you're learning the alphabet, do you get why B comes after A? Maybe. But there's not always a lot of stuff to get. Sometimes you just have to do it, and that's the biggest skill. And in this case with log laws, the biggest skill here is just being able to do this, to be able to recognize how different log expressions can look for your own ease in solving equations and making sense of expressions, but also so that you're not blindsided when you see something that's equivalent that's written a different way. A lot of times calculus students get tripped up on log laws when it's just really rewriting something a different way, like a synonym. Okay, the first one. I'm talking too long about it. The first one is if I multiply the things together that are inside the logs, I can add together the logs. This is the equivalent rule to if I had like 3 squared times 3 to the 4th, that would be saying 3 to the 6th. So remember that a log asks, what is the exponent? Okay, if I had the base 3 log of 3 squared, it's like, what is the exponent on 3 squared? This is stupid. If I had the base 3 log of 3 to the 4th, what is the exponent on 3? It's 4. And the base 3 log of 3 to the 2 times 3 to the 4. What exponent would I put on 3 in order to get that? It would be 6. I add them together. Okay. If this is multiplied, if inside the log they're multiplied, when I go outside the log, I just go down 1 level in the order of operations. So from times, I go down to plus. The next one's really similar. If I've got divided by, it's minus. And this is the equivalent expression, the equivalent rule to if I had x to the 7th over x to the 5th, I know that that would be x squared. I subtract the exponents. And you can convince yourself of that in the same way that we did with that other one. If a log asks, what's the exponent? When I divide things that would have a common base, I would subtract the exponents on them. This is one exponent, that's another exponent, I subtract them. The last one, if I have an expression to a power inside the log and the whole expression is to that power, then I can bring that power down in front. And this one's a little bit tricky to make sense of, but it's the equivalent expression to like, let's do 10 here. If I said 10 squared to the 6th, that would end up being 10 to the 12th. Okay, so if I had, that's like the base 10 log of 10 to the 2 to the 6 is 6 times the base 10 log of 10 to the 2. You get that? Like this is an exponent because it was an exponent here. A log is an exponent. And when I have an exponent to an exponent, I multiply them. So I'm multiplying the exponents here. Let's see these three log laws in action. We're going to do three things with them. We're going to be given condensed expressions and asked to make them longer and expand them, and getting rid of all the junk that's inside the logs. We're going to be given those long spread out expressions and asked to condense them. And you're like, well, which one is it? Are we supposed to condense them or are we supposed to expand them? And really both. Like this is like translation. You just want to be fluent with seeing one log expression and knowing that it's equivalent to another way that that log expression could be written, because it will be advantageous for you to know both kinds. And then the last thing we'll do is to solve a couple of equations. We might just end up solving the one equation here today. I don't want to take it too long. Here, example number 1, we're expanding, and you'll notice I have all multiplication to start with. So I'm going to do, we always start with laws 1 and 2 when we're expanding. Log law 1 says I can add these things. If I'm multiplying inside the log, I can add the expressions with new logs. And notice how I wrote a log. When I add a plus, I make a new log. And now I can apply log law 3. This one's got no exponent on it, so don't worry about it. These last two have exponents on them. So log 12 plus 5 logs of x. I'm going to write -2, like -2 logs of y. That's really like plus -2 times log y. And that's my expanded form. Let's do number 2. I'm going to start with the division, always starting with log law 1 or 2. This will give me the natural log of x squared minus the natural log of the square root of 4x plus 1. And now you know your exponent rules. I'm sure you would know this, but I'm going to tell you anyway. So the square root is like saying 2 to the 1/2. And now I can apply log law 3. Powers come down in front. And now I've got 2 natural logs of x minus 1/2 natural log of 4x plus 1. And I'm done. I'm going to resist the temptation to try and split this up because there's a plus in there. If you've got a plus or minus inside the stuff, that's the kiss of death. That means you're done. Because our log laws, if we look at these, log laws are about taking expressions that have multiplication, division, and powers, not taking expressions that have plus, minus, and that kind of thing in there, right? So all right, we don't need to do more of those examples, but let's jump into condensing. So now I've got some long written out ones, and I'm going to smush those together. And now I'm going to go in reverse order. I'm going to do log law 3 first. So that turns this one into the base 3 log of x to the 4th minus the base 3 log of x plus 6 to the 1/3. And just like last time, I'm going to change that 1/3 power into a root. Bam. All right, and now I've got this minus here, so I can use log law 2 kind of in reverse. I'm going to have the base 3 log. Now I have 1 log, base 3 log of x to the 4th over the cube root of x plus 6. When you're condensing, it's real easy to know when you're done when you're condensing, because you'll have 1 logarithm. You should end up with a single log, and then everything condensed like inside the argument or inside the expression of that log. Let's choose one more of these guys. They're all kind of the same. Let's do number 2. Exponents first, and I just have the one of them. So I get the natural log of 3x plus 5 minus the natural log of x to the 4th minus the natural log of x minus 1. Now in my class, I just say log. We use natural log. If you're in pre-calc, you probably don't know this yet, but once you hit calculus, like nobody cares about logs of other bases at all. Like e is the best exponent when we're talking about exponential functions. Y equals e to the x is really the king of all the exponential functions. He's the only one we really care about. For very calculus-y reasons. You can look up the reason why this function is special. Actually has to do a lot with the guy who it's named after, is Leonard Euler. So if you ever want a research topic, if you're doing an English paper or something and you need a guy to look up a biography, look up Leonard Euler and e to the x. So anyway, e to the x is so special. None of the other exponential functions are as cool as e to the x, and therefore none of the other logarithms are as special as natural log, which is the base e log. So anyway, we just call it log in my class, but I'll say natural log for the rest of this problem. Taking care of log law 3. Now we go to log laws 1 and 2, and these are both minus, and I'm not going to overthink it. That means that both of those expressions, x to the 4th and x minus 1, they both end up in the denominator, okay? It's not the kind of thing where like it's minus and then minus, so it ends up back on the top, and you know the reciprocal of the reciprocal is the original. It's not that, because it's not this. If I had bigger parentheses around there where I was actually taking a quotient and putting it in a quotient, then I would worry about that. But if there's just a single negative sign, that expression is going to end up in the denominator. And I only have one log, so I know I'm done. All right, last but not least, we're going to solve an equation. Sometimes we're going to come back to this one. Sometimes solving an equation, like these guys, you probably have a calculator where you can plug it in. You can just ask your calculator for the base 5 log of 12. It's really what we want here. If I was going to rewrite this with a log expression, it would say the base 5 log of 12 equals x. That's just a straight up definition, applying the definition of logarithms. But long ago, before calculators did things like that for us, we would use this strategy. You pick your favorite log. Mine's always or a natural log. I put my favorite log on both sides, and then by log law 3, I can pull that x out in front. X times the natural log of 5 equals the natural log of 12. This is a number. That's a number. Type them in my calculator, do a little dividerino. And without looking at my calculator, I don't know what the numeric value of this is going to be, but that would be my answer. I'm not going to cancel the logs. I can't cancel logs. They're not numbers. I'm not going to use a log law here because I don't have a log of a quotient. I have a quotient of logarithms. So I'm not trying to condense it as one log. This is just my answer. Log 12 over log 5. That's how I would get x. Sometimes we call that the change of base rule. If you're asked to evaluate the base b log of c and you don't have a calculator that can do that easily, you just type in the natural log of c, the natural log of b, and you divide them. It's very easy for me to remember because B stands for basement. Like the base stays in the basement. See how that works? It's on the bottom, ends in the bottom. All right. Yeah, we're going to skip those, but we're going to go back here and solve one of these equations, one more of these where log laws are going to help us in kind of a more direct way. I cannot cancel the logs here because like I can't divide by log. It's not a number. It's not an expression that I'm multiplying by. So I need to combine. I can cancel them. If I had log of one thing equals the log of another thing, then I'm allowed to cancel the log because basically what I'm doing is taking 10 to both sides and that cancels out that log. So I need to use a log law to condense this so that I have a single logarithm expression on the left side. And because it's plus, I'm going to make that times, use log law 1, log of x times 3x equals the log of 12. Now I can cancel the logs. X times 3x would be 3x squared, and I get 3x squared equals 12. Now I can solve like I'm in an algebra class. X squared equals 4, and x equals positive 2 or negative 2. But wait, there's more. In logland, it's always important that you check your answers, right? But in logland, it's really, really important that you check your answers. If I plug this positive 2 back in here for every x, I get the log of 2 plus the log of 6, and you can check that on your calculator. It does indeed equal the log of 12. Hunky dunky, everybody's happy. If I plug in negative 2, the log of negative 2 plus the log of negative 6, your calculator should blow up. You can't take logarithms of negative numbers. Logs are only defined for positive numbers. You can't even take the log of 0. Logs are only defined for positive numbers. So the log of negative 2 is nothing, and this whole equation would be nonsense if I try and plug in negative 2, and it is not a solution. So when you do log equations like this where you end up with, even if you only end up with one solution, but especially if you end up with multiple solutions, it's really important to go back and plug those numbers in, verify that they make sense in the context of the original, to go back to the very original form of the equation, and then just make sure that your answers are sensical and not nonsense. All right, that's it for log laws. I hope you found this helpful. Don't forget to like and subscribe. Hope to see you next time.